Modeling is simple. Modeling is exactly as before. So there's no challenge in modeling. Let's say that from an output perspective, what do we assume? And how does the group thing really come into being? So again, a simple map. That's a group of friends. And that's another group of friends. Now, let's take one of the entities separately and see what will happen. So that's one entity. Now, if this guy is friends with this, it'll have an attraction, a very strong because it's leaving out. On the other hand, if this guy is not a friend with this group, might even have a repulsion, doesn't know, getting very close to one member. So the distance which earlier you saw was large, now suddenly becomes small. Because friends have very small social distance between each other, so it's more towards the attraction side. However, for non-acquaintances, this is too small a distance, so that's repulsion. Similarly, if we look at around over here and we guess what the behavior should be, now naturally what will happen is if all of these are friends, then these three people will actually go like this and all these people will go like this because nobody wants to cut each other. These three people don't want to cut this group, split it into half. On the other hand, if these people were not related to each other, they would actually expand out because of small distances between each other, giving an indication that this three people should actually go from between. Why they stay intact? Because they are friends. So, how do the two groups attract or repel? And the behavior which is displayed is essentially a function of the affinity between the groups. Take a strong example. A couple is walking around over here and don't do it, but take it as a challenge. You're going here, try to walk in between these two people. Just try to see what happens. So try to intercept a couple, what happens. At the same time, two people not connected to each other are walking towards each other and try to intercept them and see what happens. So here you won't be able to do it, and here it will be most easy to do it. In fact, they might also go like this because the distance between them is a bit too small. So, how groups behave is entirely a function of their acquaintance level, and that's a kind of force that they exert. Now let's go back to the old potential field and say that these two people did not feel a force towards each other. Which couple do you see works like this? So there's a force which is binding them together, and that's the attraction force. The other example, so something that's very hard to do. I say that this is a queue of people who are going to buy a ticket to a museum or something, and this is you. Now, of course, you'll tell this guy, I just want to cross. This guy will say, okay, and you go here. But if these two people were the same family, then the moment you try to intercept them up, the more this guy or the girl gets close by. Strong attraction. And indicates that you should go here. The worst is if all of them were school kids. They never let you pass by. You'll have to bang your head, call the teacher. Small kids, strongest attraction between each other. So that's what attraction and repulsion can make a difference. Taking at the macroscopic level as well. So groups over here. So the molecules of the same kind will bind each other pretty nicely, and if you want to cut them in between, it's going to be extremely difficult to do so. That's because the molecules bind each other up. There's a socialistic distance if there are humans involved. Even molecules cannot come ridiculously close to each other. And studying all this thing and simulating this up is what we call as the social potential field, and it's important because of exactly the same reason. So that's important because if you don't consider these social factors, it may appear that no chaos is gonna happen, but the chaos will happen because a family will not let anybody pass through. And therefore, it's modeling this attraction is an integral part of any simulation. Now, let's study speed as well as a factor. So, that's my first agent. So, that's one. And there are other agents which are around. So let's first have this agent, and that's what's the orientation direction of this person. Now, it so happens that how these two people behave is entirely a function of their relative speed. If this person walking very fast, this person doesn't consider this. No force because of this. No collision is about to happen. On the other hand, if this person is static, then the forces are to avoid like this. On the other hand, if this force is coming around over here, then you go around over here. So many ways to model it up. One uses relative velocity as calculation. The other says simulate the two up. The effective force is where the two people are at the closest proximity or they collide. So many modeling which makes this possible. But the important thing is to consider the relative speed of both of them. Then consider the spatial orientation. A funny thing happens in driving. When you have a vehicle in front of you, you maintain enough distance. So it's a few meters, the distance between your front bonnet and the front vehicle's back bonnet, but at the side it suddenly becomes half a meter. So in driving in front, you are very cautious about somebody coming in within half a meter. You never let that happen. Side by side, you're at half a meter's distance, you don't care, it's enough. Back you don't care upon at all. So how many times do you see at the rear view mirror and see that there's a guy? You say it's his responsibility. You don't even care about it. So that's another factor that comes into play where the orientation or the spatial position, it plays a role in what the force or what the value should be. Now I don't do all the modeling. It was just a food for thought. So it was just about the different things that you see, and I let you practice this up, give you some questions and see if you can have those effects simulated, if you can control the coefficients and have those simulations experienced by yourself. What I will do is that I'll just give you one general modeling. So let's remodel attraction and the repulsion forces. The first one, let's say attraction. So that's my goal. This is my robot, which is currently traveling in this direction, which is with a speed of v. Now this is the current speed. This is the speed at the current time. And I desire to travel in this direction. So let this be a unit vector E, where a unit vector E is of course given by goal minus q divided by dq comma goal, a unit vector in the direction. The vector goal minus q and divided by the magnitude. Now the best thing that I can do is I move with a velocity, and here when I say the velocity I mean a vector quantity. Previously I was using a scalar quantity, now for the first time I use a vector quantity. This is what is my ideal best velocity vector. So it has a maximum speed possible, Vmax, whatever you drive, 60 kilometer per hour, however you walk, 10, I mean not 10 kilometer per hour. And this is the direction where you want to go. Now, what is force? Force is mass into acceleration, where mass is virtual, can be subsumed in the other parameters. So it's acceleration. Acceleration is my desired velocity minus my current velocity and the time in which I want to get to my desired velocity, and that is exactly what I say is the F attraction towards the goal. As a vector, it will produce the best velocity vector, and therefore I take this as my ideal direction to goal force. The beautiful thing is that if I'm traveling, maintaining a speed of v max in the direction of E, this term gets 0 and there is no attraction force because I'm already traveling with the best speed possible towards the goal. Just continue walking and you'll get to the goal. Now, interesting part of it, of course, which is repulsion force. Let me remodel it up. The repulsion force that we saw has actually a problem. When the distance is very large, force is 0, distance is large, force is 0, distance is large, force is 0, distance is large, force is 0. But 1 upon d cube, it behaves like this. It suddenly becomes infinity. And that's what bugs in digital simulation that we do. I simulated here 0, here something which wasn't effective, here something which wasn't effective, here infinity. So you either get almost 0 or you get infinity, and that bugs off people's mind. So people want to just get rid of infinity. I want to get rid of infinity. I've stopped using d cube. You get infinity very quickly and then you just hate that up. So another curve, a very similar curve is A, it's smooth, and B, it doesn't have an infinite problem. And of course I'm talking about the exponential. So instead of both model the inverse, it's just that this is A, it's smoother, and B, it doesn't give you infinity. That's the magnitude, and then the direction is of course q minus o divided by t q comma o. So it's not that I'm writing down a new equation in this one specifically. All that I'm doing is that I hate infinity and stopped using that up. So I like the exponential, it doesn't give that infinity problem. So this one shows a smoother trend and this one shows a more interesting pattern. So it's the same inverse otherwise, whether you use model inverse by exponential or you model inverse by 1 upon d cube, it's a similar thing. But